Have you ever looked at one of those amazing, crystal clear satellite photos of Earth and just wondered, how do they get it so perfect? Well, let me tell you, it's not as easy as pointing a camera out of a spaceship and clicking a button. Today, we're going to dive into the essential cleanup process. It's called preprocessing, and it's how we turn raw, messy satellite data into the beautiful and scientifically accurate images that help us make sense of our planet.
So let's start with the big question, right? Why isn't that raw picture the satellite takes instantly a map? I mean, it's a photo of the Earth. Shouldn't it just work?
Well, the reality is a whole lot messier. Think of it this way. Taking a satellite image is kind of like trying to snap a perfect photo from a speeding roller coaster while looking through a warped, dirty window. Seriously, the satellite is screaming through space at thousands of miles an hour, the Earth is spinning underneath it, and you've got the entire atmosphere getting in the way. The result? A picture that's warped, full of noise, and just not lined up with reality.
So our first big job is to fix all those warps and wobbles. We need to digitally untwist and stretch the image so that it has the same perfect geometry of a map. This is where we start to make things right.
And the official name for this is geometric correction. It's all about taking that raw data and digitally wrangling it to get rid of the distortions. The main goal here, the whole point, is to make sure every single pixel in that image lines up perfectly with its actual location on the ground. This creates a rock-solid foundation for everything else we want to do.
So what's causing all this mess in the first place? Oh, it's a whole bunch of things all happening at once. You've got the Earth's rotation and its curve, for starters. But then the satellite itself isn't perfectly steady. It's got tiny little movements, roll, pitch, and yaw, kind of like a boat on the ocean. All of these things add up to create an image that is seriously stretched out of shape compared to the real world.
And this visualizes our goal perfectly. Over on the left, you've got that raw, warped grid, just like the sensor saw it. And on the right, that's what we want, a perfect, uniform map grid. The whole game of geometric correction is using math to turn the image on the left into the map on the right.
So how do we pull that off with any kind of accuracy? The secret ingredient is something called ground control points, or GCPs. You can think of these as our anchors to reality. A GCP is just a feature on the ground that's easy to spot, like a specific intersection of two roads or the corner of a building. And crucially, we know its exact real-world coordinates. By finding these points in our wonky image and telling the computer, hey, this point actually belongs over here, we can figure out the exact transformation we need to apply to the whole picture.
Now, this whole thing follows a very clear process. It's not just guesswork. First, you choose your correction method. Then, you use those GCPs we just talked about to lock in the mathematical parameters. After that, you've got to check your accuracy to make sure it worked. And finally, you do a step called resampling to build the brand new, corrected image.
So how does the computer actually do this stretching? It's not magic, it's math. It uses these really clever mathematical models called polynomial transformations. These are basically just fancy equations that describe the distortion. By plugging in our GCPs, the software can solve these equations and figure out precisely how to push, pull, and rotate every single pixel into its correct spot on the map.
Okay, so once we've built that perfect new map grid, there's a problem. It's empty. We need to fill it in with all the color and brightness data from our original distorted image. That process is called resampling. We are literally going through and calculating a new brightness value for every single pixel in our new corrected grid.
And there are a few ways to do this, and you really have to pick the right tool for the job. Nearest neighbor is the speed demon. It just grabs the value from the closest old pixel. This is fantastic if you need to keep the original data values perfectly intact, say for classifying different types of force. Bilinear interpolation is going to give you a smoother look by averaging the 4 nearest pixels, which is often more pleasing to the eye. But if you need the sharpest, most precise result, say for a scientific study on crop health, you'll want cubic convolution. It averages a whopping 16 pixels. It takes a lot more computer power, but that precision is absolutely critical.
All right, we've done it. The image is now in the right shape and in the right place on the map. But hold on, we're not done yet. We still have to make sure the brightness and the color of each pixel are actually telling us the truth about what's on the ground. This next stage is called radiometric correction. So if geometric correction was about fixing where the pixels are, radiometric correction is all about fixing what the pixels are saying. We're trying to correct errors in the brightness values that can come from little quirks in the sensor itself or, again, from that pesky atmosphere. This is all about making the data scientifically sound.
And a really big part of this is converting the raw pixel values. See, the sensor just records an arbitrary number called a digital number, or DN. It's not a real-world unit of anything. Radiometric correction is what turns that meaningless number into surface radiance, which is a true physical measurement of energy. This is a huge deal because it's what allows scientists to compare images taken on different days or even by totally different satellites.
And just like any camera, these sensors can have glitches. Radiometric correction is designed to hunt down and fix things like line dropouts, where you get a dead black line running across your image because of a faulty detector. It also gets rid of banding or stripping, which looks like visible stripes, and it cleans up any random salt and pepper noise.
Okay, we've fixed the geometry, we've corrected the brightness of the pixels. There's just one last big hurdle to get over, and that's the atmosphere itself.
Right, that column of air between the ground and the satellite isn't empty space. It's full of dust, water vapor, and gases that mess with the light. They scatter it and absorb it. You know how on a hazy day, things far away look kind of blurry and blue? It's basically that, but the satellite is looking through the entire atmosphere. It washes out the image and changes the true brightness of things on the ground.
And the solution, you guessed it, is atmosphere correction. This is some seriously sophisticated stuff. It uses physical models to basically calculate the effect the atmosphere had on the light as it traveled to the sensor. Then it subtracts that effect from the image, giving us the true surface reflectance, or what the satellite would have seen if there were no atmosphere at all. Pretty amazing.
So, after all of that, after fixing the shape, correcting the brightness, and basically peeling away the atmospheric haze, what have we actually accomplished?
We've taken what was essentially a stream of raw, unusable data and turned it into something incredibly valuable. Preprocessing transforms those distorted, noisy numbers into a faithful, accurate, and scientifically valid picture of what's happening on the Earth's surface.
The source material from Utrecht Open University just says it perfectly. The goal of all of this is to correct all that distorted and degraded data to create a faithful representation of the original scene. That's it. That's the whole ballgame, getting rid of all the errors to see what's really there.
It is a ton of work, no doubt about it. But this clean, corrected data is the bedrock for pretty much everything we do in remote sensing. From tracking wildfires and monitoring deforestation to managing our farms and responding to natural disasters. Which, of course, leads to the really exciting question. Now that the image is clean, what secrets about our planet can we finally unlock?